This is Mrs. Palmer Quay with the first video for Module 12. In this video I want to go through some of the basic properties of gases. The molecules of any substance in the gas phase are widely separated. There's about 10 times the space between each molecules as the molecule itself. Because of that distance in between molecules of gases, intermolecular attraction, the forces of molecules being attracted to each other, which is quite important to determine the properties of solids and liquids, but in gases, intermolecular attraction really doesn't have very much effect, and also as a result, gases generally have low density. This separation of the particles of the gas mean that gases expand to fill any container. You can think really that a particle of gas is out to travel to the farthest reaches of the universe, and it's only stopped by some other force, either reaching the side of a container or being held back by gravity. As these gases expand, they exert pressure on the sides of the container. We can also compress gases. We can make them fit into a smaller space, which is impossible to do with liquids, and solids can compress if they have air space between their solid substance, like a piece of bread you can compress. But individually, looking at individual molecules, they're so close together in solids that there's not really a compression factor. But you can compress gases quite a bit. And gases can easily diffuse into each other, and so they mix together very well. The kinetic molecular theory, or the kinetic theory of matter, tells us that all atoms or molecules or particles are in motion, and that it is this motion that determines whether they are existing as a solid, a liquid, or a gas at any given temperature. Gas particles are moving rapidly and in straight lines until they collide with something. This collision allows them to bounce off, whether they are bouncing off each other or the walls of the container, and it is these collisions with the walls of a container that result in the pressure of the gas. This little illustration here shows our gas particles moving in the direction of the arrow, and as they bump into the sides, then they are colliding and changing direction, going off into head out, in another way till it collides into another particle or another side of the container. So when you add up all the forces of all the particles colliding on the walls of your container, you get the total pressure. In this illustration of the balloon is held out in its nice circular balloon shape because of the pressure that's being exerted by the helium molecules that are inside the balloon. And this pressure has to be greater than the atmospheric pressure that's being exerted on the balloon from the molecules of air that are bouncing around out here. When the situation is greater inside than outside, you have a nice round balloon. As you lose helium, your balloon deflates, and it'll get to a point where the pressure inside and outside is equal. We can measure pressure in a number of different ways. We measure it as atmospheres, and typically at sea level we're approximately 1 atmosphere. It also can be measured as kilopascals, and so 101.3 kilopascals is equal to 1 atmosphere. We can measure atmosphere in torrs. 760 torr give you 1 atmosphere. Millimeters of mercury correlate with torr, so you have a 760 millimeters of mercury equaling 1 atmosphere. And then 2 other measurements that are not mentioned in your textbook but you might see are the millibar. If we went and got the atmospheric data from the airport's website, it will give us the air pressure, the atmospheric pressure in millibars, and it's 1013 millibars equaling 1 atmosphere. So if you look at the millibar number and the kilopascal number up above, you might be able to guess that there is a relationship between these millibars and kilopascals, and that's true. And then if you are inflating your tires on your car or your bicycle, you'll be measuring things in pounds per square inch, or PSI. And so 14.7 PSI are equal to 1 atmosphere. When we measure atmospheric pressure, we're using a device called a barometer, and there's just a simple example over here of what's happening in a mercury barometer. You have a pan of mercury down below going into a tube that has the 760 plus millimeters marked out on it. This is actual millimeters, it's actual height measured here. And as the atmospheric pressure pushes down on this flat open surface of Mercury, then the mercury level inside this tube will increase or decrease depending upon how the pressure changes, giving us a reading. So a barometer is measuring atmospheric pressure by something similar to this mercury barometer that we see here. There are a number of factors that can affect the pressure of a gas. Logically, the amount of gas will determine the pressure. If you have more moles of a gas present in a container, then the pressure is going to go up because there are more particles to crash into the side, and it's the sum of all those collisions that determine the pressure. The volume of the container will also have an effect on the pressure. If you compress the gas by decreasing the volume, then you increase the pressure. And then the temperature of the gas is a third thing that affects pressure. As you increase temperature, you increase the kinetic energy of the gas, and so the particles are moving with more speed, which translates to more force when they collide into the walls of the container, and the overall pressure increases. These three illustrations give you an idea of the interdependency between pressure and volume and temperature and number of gas particles. The first picture here on the left is showing us pressure versus volume, and this is specifically delineated in Boyle's law that we will talk about in the next video. But at a constant temperature and a constant amount of gas, if you change the volume, so if you take this little movable plunger and make the volume of the container larger, the pressure will go down because your few particles are spread out over a greater amount of volume. The relationship between volume and temperature is outlined in Charles's law, which we also will talk about in the next video. And Charles's law tells you that at a constant pressure and a constant amount of gas, the same number of moles of a gas, when you increase the temperature, you increase the volume, because you can see we've got faster moving particles here. They have a little bit longer tails. You look like little comets or tadpoles. And so when there's greater kinetic energy, the temperature has gone up. Then in order to maintain the same pressure, you've got to increase the volume. And then the last one, Avogadro's law, is not covered by your textbook. This is the same Avogadro that gave us the number for the mole. And it is talking about the number of particles, the moles of particle, as you might assume. So at a constant pressure and a constant temperature, if you add more moles of particles, so you can see we have about twice as many particles over here on the right as there is on the left, and that also will cause our volume to increase. So we have these relationships going on between the pressure and the volume and the temperature and the number of moles in the gas that we'll be working with throughout this module. So this finishes what I want to cover on basic gas properties. We'll be looking at some of the gas laws in our next video.